Hello students, in last class we already studied about what is lens, different types of lenses and how to derive the lens maker formula for a thin lens. Clear? So we already studied that the given lens maker formula for a thin lens is 1 by V minus 1 by U, which is equal to the focal length, which can be written as refractive index of the lens divided by refractive index of the medium whole into 1 by R1 minus 1 by R2. Clear? This is the given formula. We already derived it in the last class. So what is V? V is the image distance, U is the object distance, F is the focal length of the given lens. This is the refractive index of the lens medium, this is the refractive index of the surrounding. R1 is the radius of curvature of one spherical refracting surface and R2 is the radius of curvature of the second spherical refracting surface, because lens is a optical instrument which have two refracting surfaces, either one of them must be spherical. So if two surface of the lens are spherical like this, it will be a convex lens. If the two surfaces are spherical like this, it will be a concave lens. Clear? So whenever the light incident one of the spherical surface for the first, that radius of curvature is known as R1 and the other one is known as R2. If this is the principal axis and object is here and the incident ray first strikes this spherical surface, then the radius of this one will be R1 and this one will be R2. Similarly, if the incident ray first strikes this spherical surface, the radius of this one will be R1 and this one will be R2. Similarly, if object is here and the incident ray first strikes this spherical surface, its radius of curvature will be R1 and it will be R2. So R1 is the radius of curvature of that spherical surface on which the incident ray strikes first, and R2 will be the radius of curvature of the other spherical refracting surface of the given lens. Clear? And here all are used with respect to the proper sign convention during its application in the numericals. Clear? And the sign convention is same as that of the spherical mirror, because all the optical instruments have common sign convention. If we measure anything along the direction of incident ray, it will be positive. Opposite to it will be negative. Anything measured above the principal axis, it will be positive. Below the principal axis, it will be negative. Clear? And to apply this formula is only applicable when the rays are paraxial. You have to remember that. And generally in ray optics we deal with all the formulas only when the rays are paraxial. When rays are paraxial, next the lens should be thin. That means if this is the lens, this thickness will be very negligible and both sides of the lens have same medium. Both sides of the lens have same medium. Clear? These are the conditions only when this formula is valid. Clear? So next we are going to discuss about what are the different conditions of incident rays and refracted rays through a lens. So basically we know the complete lens is of two types. We already know lens are basically divided into different types. Okay, so these type of lens, okay, let it be M dash. If this type of lens where both the refracting surface are convex in nature, this one is convex and this one also convex, then it is known as a biconvex lens. Okay, the radius of curvature of this one is R1, let it be this one is R2, or you can choose R1 or R2 depending upon the incident ray. If here is a object and the incident strikes at this surface, it will be taken as R1 and the other one is taken as R2. So this is biconvex lens. If both the ends are concave and object first strikes this surface, so the radius of curvature of this one will be R1, this one will be R2, so it is biconcave. Clear? And if R1 equal to R2, then it will become equiconvex. Here also if R1 equal to R2, that means radius of curvature of both the spherical refracting surface is equal, it will be equiconcave. Okay, if one of them is convex and other one is plane, then here if right rays strike along this direction, it will be R1 and it will be R2. So here R1 and R2 equal to how much? Infinite, because it is a plane spherical surface or it is a part of a large spherical sphere which have radius infinite. So here it will be planoconvex. Similarly, if one side is concave, other side is plane, and light strikes along this direction, so it will be R1, this one will be R2, which is equal to infinite, it will be planoconcave. Clear? And if both the ends, one is concave, another one is convex, like this, and this one is R1, this one is R2, light strikes from this direction, so it will be concave or convex, or you can say convex or concave. Okay, so these are the different types of lenses according to their refracting surfaces. Clear? And by the using R1 and R2, we can find out the focal length of the given lenses by using the lens maker formula, which is equal to refractive index of the lens divided by refractive index of the surrounding medium minus 1 into 1 by R1 minus 1 by R2, and R1 R2 you can choose by depending on the incident rays. Clear? And all have to use with sign convention. Clear? Next, lens can be divided into two types. One is converging lens and another one is diverging lens. Okay, all the lenses that we studied are categorized into two types. One is converging lens, another one is diverging lens. So what is converging lens? The lens which converge the incident rays after refraction. Diverging lens, the lens which diverge the incident ray after refraction. Okay, so if this is a lens, it's a convex lens. If here is a object, incident rays are coming like this, so after refraction they will converge at this point. Clear? And if this is a lens, rays are coming like this, after refraction they will go like this, so they get diverged. So this is a converging lens, this is a diverging lens. So basically in many of the books it is mentioned that a convex lens as a converging lens is equal to converging lens, and a concave lens as a diverging lens. Okay, but this term, a convex lens is a converging lens and a concave lens is a diverging lens. It's not always true. You have to remember this. In most of the books, it was mentioned that convex lens is a converging lens, concave lens is a diverging lens, but it's not true always. Always a convex lens is not converging and a concave lens is not diverging. Most of the cases, a convex lens is a converging lens and a concave lens is a diverging lens, but not always. Okay, this happens only when a convex lens is a converging lens, only when refractive index of the surrounding is less than refractive index of the lens. You have to remember this. Okay, only when the refractive index of the surrounding is less than that of the lens, a convex lens can be a converging lens and a concave lens can be a diverging lens. Only when you have to remember that these two cases, a convex lens can behave as a converging lens and a concave lens can behave as a diverging lens, only when the refractive index of the surrounding medium is less than that of the lens medium. Clear? But when it's interchange, that means refractive index of the lens medium is less than refractive index of the surrounding medium, a convex lens can behave as a diverging lens and a concave lens can behave as a converging lens. Clear? So you have to remember this. A convex lens and a concave lens can behave as a converging lens and diverging lens respectively only when the refractive index of the surrounding medium is less than that of the lens medium. But when the refractive index of the surrounding medium increases in comparison to the refractive index of the lens medium, the converging lens, which is known as concave lens, can be the diverging lens, which is known as concave lens, can be converging, and the converging lens, which is known as convex lens, can be diverging. So it is not always true that we can easily say that a convex lens is a converging lens or a concave lens is a diverging lens. So any one of them can be converging, can be diverging depending upon the refractive index. So basically, what is converging lens? The lens which converges the incident ray after refraction, and the diverging lens is the lens which divert or diverge your incident ray after refraction. It may be convex lens, it may be concave lens depending upon the situation. Okay, so whenever you have to answer that what is converging and what is diverging lens, converging lens is the lens which converges the incident ray after refraction and diverging lens is the lens which diverges the incident ray after refraction. But never say that a convex lens as a converging lens or a concave lens as a diverging lens, because a convex lens can also behave as a diverging lens and a concave lens can also behaving as a converging lens. Okay, depending upon the refractive indices. Clear? So you have to remember that both concave and convex lens can behave as both converging and diverging lens. Clear? But most of the cases, convex lens are converging and concave lens are diverging. Okay, so we already know that all the lenses are divided into two categories. One is converging and another is diverging. So what is the symbol of converging lens? A converging lens can be symbolically represented as like this: a thin converging lens. This is the symbolical representation in case of ray optics for a thin converging lens. What is the symbolical representation of a diverging lens? This is the symbolical representation of a thin diverging lens. Okay, this is the converging lens, this is the diverging lens. It may be concave or convex, it can also may be concave or convex. Clear? Depending upon the refractive index of the lens medium and the surrounding medium. Clear? You have to remember this. So as each lens, if it is a concave or convex, this is a convex lens, let it be biconvex lens, and it is a concave lens. biconcave. Okay, so there are some terms related to each lens. So as this is a lens, let will be L dash. This is also L dash. Okay, so convex lens are those lenses which are thicker at the middle and thinner at the edges. Concave lens are the lenses which are thin at the middle and thicker at the edges. Clear? So these lenses have two refracting surfaces which are spherical in nature. Okay, in this case both are convex, in this case both are concave. So there are certain terms related to this. If this is the concave part of a sphere, so it will also have a radius center of curvature. Let this be C1 and its radius be R1. And similarly, if this is a part of a spherical sphere, it also have a center of curvature. This is C2 and its radius be R2. Clear? So the line which joins both the center of curvature or passing through both the center of curvature is known as principal axis or optical axis. The line joining both center of curvature is known as principal axis. Here also the center of curvature, this is C1, this is the center of curvature C2. So the line joining these two center of curvature is known as principal axis. Okay, principal axis let it be denoted by x dash x, x dash x. Clear? Denoted by x dash x. Clear? And there is a point in each lens. Okay, any incident ray passing through that point goes undeviated. If this is the incident ray and this is passing through this point, it goes undeviated after refraction. In each lens there is a single point. Any incident ray passing through that point goes undeviated, and that is known as O or optical center. Okay, in each lens or every lens there is a point through which if any incident ray passes, goes undeviated after refraction, this is known as optical center or pole of lens, denoted by O. Clear? There is a single point, any incident ray passing through that point goes undeviated after refraction, that is known as optical center or pole of lens, which is denoted by O. Clear? Again, as lens is made of two spherical refracting surface, there will be two focus because there are two center of curvature. So there are two focus which are the midpoint of the radius of curvature. Clear? If this one is C1, so this will be F1. If this one is C2, this will be F2. In both the cases, there are two midpoint of the center of curvature which are the focus for the two spherical refracting surface. One is F1, another one is F2. Clear? So every lens has two focus. Okay, or two foci, as each are made up of two refracting surfaces. So both have two center of curvatures, two radius of curvatures R1 and R2, and two, this is R1, this is R2, and similarly two focus. So one of the two focus or these two focus are categorized in two parts. One is primary focus and the other one is secondary focus. Okay, so each lens have two focus, one is primary focus and the other one is secondary focus, because both have two radius of curvatures and 2 center of curvature depending upon the 2 refracting surfaces. So what is primary focus and what is secondary focus? So you have to remember these terms. What is optical center, what is center of curvature, you already know. What is radius of curvature, you already know. What is principal axis. Then we have to study what is primary focus and what is secondary focus. Okay, so now we are going to discuss what is primary focus. So primary focus is such a point on the principal axis of a lens. If it's a lens, the primary focus is such a point on the principal axis of a lens from which the incident rays are diverging and after refraction goes parallel to the principal axis. In case of convex lens, and in case of concave lens, the incident rays appear to converge and after refraction they goes parallel to the principal axis. So for concave lens, the primary focus is such a point for which the incident rays appear to converge from and after refraction goes parallel to the principal axis, like this. Okay, so this is F1 and this is F1. So for convex mirror lens, the primary focus is such a point from which the incident rays are diverging and after refraction goes parallel to the principal axis. And for concave lens, the primary focus is such a point at which the incident rays appear to converging and after refraction goes parallel to the principal axis. So what is primary focus? It is a point on the principal axis of the lens from which the incident rays are diverging or appears to converge after refraction appears to converge at, okay, it is a point on the principal axis of the lens from which the incident rays are diverging or appear to converge at will goes parallel to the principal axis after refraction through lens. Okay, so it is a point on the principal axis of the lens from which the incident rays are diverging or appear to converge at will goes parallel to the principal axis after refraction through the lens. Clear? This is known as the primary focus. Okay, then what is secondary focus? So secondary focus is such a point at which the incident rays coming parallel to the principal axis of a lens are converges or appear to diverge from. So if the incident rays are coming parallel to the principal axis and after refraction they converge at a point, so this point is known as the focus, which is known as the secondary focus. Or this is for convex lens. And for concave lens, if the incident rays are coming parallel to the principal axis After refraction they will goes like this. So they are appear to diverge from a point. This is known as the secondary focus. Clear? So in case of secondary focus, the parallel incident rays are actually converge at a point. In case of convex lens, that is known as secondary focus of the convex lens, or in case of concave lens, the parallel incident rays after refraction appear to diverge from a point. The refracted rays are appear to diverge from a point, that is known as the secondary focus. So this is for concave lens and this is for convex lens. So what is secondary focus? It is a point on the principal axis of the lens at which the incident rays coming parallel to the principal axis after refraction converges or appear to diverge from. Okay, so it is such a point on the principal axis of the lens at which the incident rays coming parallel to the principal axis after refraction converges or appear to diverge from. So this will be the secondary focus. So each lens have two focus. One is primary focus. So primary focus is the point from which the incident rays after refraction goes parallel to the principal axis, and secondary focus is the point at which the parallel incident rays after refraction converges or appear to diverge from. Clear? So these are the two focus of each lens, which are known as primary and secondary focus. Clear? Conditions of incident rays and their corresponding refracted rays for a lens. Okay, so for a given lens, how incident rays becomes different in case of different refractions through a lens. Clear? Okay, so first case, when incident rays are coming parallel to the principal axis, if this is a lens, okay, this is the principal axis. You have to remember case 1, when incident rays are coming parallel to the principal axis, like this. After refraction, they will pass through the primary focus of the lens F. This is O. Clear? So any ray which is coming parallel to the principal axis after refraction pass through the focus. This is the case of convex lens. In case of concave lens, this is also seems like this. In the principal axis, rays are coming parallel. So after refraction, they will goes like this, which is appear to diverge from the focus. Clear? Second case, you have to remember all the parallel incident rays after refraction pass through the focus or appear to diverge from the focus of the lens. Okay, any incident ray which is coming parallel to the each other but not parallel to principal axis, like this. Any incident ray which is coming parallel to each other but not parallel to the principal axis after refraction will intersect at any point on the focal plane. Okay, if the rays are parallel to each other but not parallel to the principal axis, after refraction they will intersect or meet each other at any point on the focal plane, not on the focus. Okay, next, any incident ray which it starts from focus after refraction goes parallel to the principal axis. Like this. Okay, so any incident ray which starts from the focus after refraction goes parallel to the principal axis in both of the cases, which are parallel to each other but not parallel to the principal axis, will intersect each other at any point on the focal plane, and those who are parallel to each other after refraction meet at the focus. Clear? Here these are parallel to each other but not parallel to the focal plane, will meet at any point on the focal plane. Clear? And any rays that pass through the optical center goes undeviated, like this. Okay, any rays that pass through the optical center O goes undeviated after refraction. Clear? You have to remember all these points. Parallel incident rays meets at focus, those who are parallel to each other meets at any point on the focal plane. Starting from the focus, the incident ray after refraction goes parallel to the principal axis, and those who pass through the optical center goes undeviated. So these are some conditions for incident rays and their corresponding refracted rays. Clear? So next we are going to study how image is formed in case of lens. So image formation by a lens. Clear? So here is a convex lens. Okay, this is the principal axis. At L dash, this is the pole of the lens. So it have different position. Let it be minus f, minus 2f. This is the plus f. This is plus 2f, and it is extended up to plus infinite, and this is extended up to minus infinite. Clear? So here I am drawing a table for the position of object location, image location, and nature of image. Okay, object O, image I, image nature. Clear? So first, when object is at minus infinite, so if object is at minus infinite, the rays will travel parallel to the principal axis, and after refraction they will meet at the focus. If object is at minus infinite, image will be at plus f. Condition of image, real and point image. Clear? Next, if object is in between minus infinite and minus 2f, that means object in between minus infinite and minus 2f. So object in between somewhere here. This is plus f, plus 2f, minus f, minus 2f. Object is somewhere here, minus infinite and minus 2f. So rays are coming parallel to this, and after refraction the parallel pass through the focus, and it is good undivided. It will meet somewhere in between minus f and 2f. Okay, so if object is minus infinity to minus 2f, image will be in between plus f and plus 2f. Clear? If object in between minus infinity to minus 2f, image will be in plus 2f and plus f. Clear? So let me draw the table clearly. Object, image, nature of image. Okay. So first, when object is at minus infinite, image is at plus f, and nature of image is real and point. Clear? Next case, when object is between minus infinity to minus 2f, image will be between plus f to plus 2f, and nature is real, inverted and reduced in size. Clear in this case? Clear? Next, third case, when object is at minus 2f. F minus 2f plus f plus 2f. Object is at minus 2f. So image will be also formed at minus 2f and of same size. Image is also at plus 2f, real, inverted, same size. Clear? Next, when object is between minus 2f and minus f. Object in between minus 2f and minus f. So object is traveling from minus infinity towards the pole. So now object is in minus 2f and minus f. So now image will be from plus 2f in between plus infinite. So like this, when object in between minus f and minus 2f, this is plus f plus 2f. So now the image will be in between plus 2f and plus infinity, like this. Okay, so if this is AB, this is A dash, B dash, here it is AB, it is AB, here it is AB, it is A dash, B dash, and it is infinite. So here the size of image is larger in comparison to the size of object, which is inverted and real, and it lies between plus 2f and plus infinite. So real image, inverted and enlarged. Clear? The location of object is minus 2f to minus f. Image will be plus 2f to plus infinite, which is real, inverted and enlarged. Clear? Next, when object is at focus minus f. When object is at minus f, image will be at plus infinite. It is real and point, like this. This is the optic lens. This is minus f, minus 2f, plus f, plus 2f. Object is at minus f, so the incident ray after refraction will goes like this, parallel to each other. So they will meet at infinite. there goes like this, infinite. So when minus f is the object position, image will be at plus infinite, real and point. Next case, when object will lies between minus f to pole, like this. This is the pole, minus f, minus 2f, plus f, plus 2f. When object lies between minus f to pole, the image will form behind the object. If this is A, B, A dash, B dash. So image will lie between minus infinity to pole. Clear? When object travels from minus f to pole, the image will travel from minus infinity to pole. In this case, it is virtual, erect and enlarged. Clear? So when object placed in between minus f to pole, image will travel from minus infinity to pole, which is virtual, erect and enlarged. Clear? Next case, plus f, plus 2f, minus f, minus 2f. Okay. So here in this case, when object travels from pole to plus infinite, okay, when object travels from pole to plus infinite, now image will travel from pole to plus f. Okay, so here if object travels from pole to plus infinite, image will travel from pole to plus f. Okay, so if like this, this is the object, this is the image. Clear? So when the object travels from pole to plus infinite, image will travel from pole to plus f. So here image is real, erect and reduced in size. Object is virtual. Clear? So these are the conditions for image formation depending upon the different position of the object. Clear? For convex lens, and you can also derive by yourself for the concave lens. Clear? So object and image position and the condition of image during the formation. Okay, for the convex lens. So image formation by a lens, this is basically for convex lens. For concave lens, you can derive by yourself. Clear? Next, we are going to derive the lens formula for different cases of image formation through a convex lens and concave lens. So, thin lens formula for case 1, convex lens producing real image. Okay, so here is a convex lens. This is the principal axis, focus 2f, f 2f. Clear? We already know that if there is a object which is beyond 2f and minus infinity, it will form a real and inverted image which is it will form a real inverted image which will be formed in between f and 2f, because object is beyond minus 2f and minus infinite, so its image will be between plus f and plus 2f. So here is the image. This is real and inverted. Clear? So now here we have object a, b, for which the image will be a dash, b dash. This is the optical center O. Clear? So here we have two triangles ABO in triangle ABO and in triangle A dash B dash O. Let the name of the length be MM dash. Clear? So ABO and A dash B dash O triangle, these two angles are same. Angle O is opposite, or angle AOB equal to A dash O B dash due to opposite angle, and angle A equal to angle A dash 90. So both triangles are similar. Clear? As these two angles are 90 degree and this is the equal angle due to opposite angle, these two triangles AOB and A dash OB dash are similar. That's why the corresponding ratio of the corresponding sides will be same. So we can write both the triangles are similar. So we can write AB divided by A dash B dash will be equal to AO divided by A dash O. Let it be equation 1. Clear? Similarly, if MO is nearly equal to AB, because this is the parallel ray which is parallel to principal axis, that's why if AB must be nearly equal to MO, because the ray comes parallel to the principal axis. Similarly, if MO is nearly equal to AB, then you can write in the triangle MOF and let it be A dash B dash F in triangle A dash B dash F. So this is the triangle MOF and A dash B dash F. These F angle are opposite to each other. Angle MFO equal to angle A dash F B dash. Due to opposite angle MFO, O is 90 degree and angle O equal to angle A dash equal to 90 degree. So these two triangles MOF and A dash B dash F are also similar. So both triangles are similar. So the corresponding ratio of the side will be same. So OM divided by A dash B dash equal to OF divided by A dash F. Equation 2. But as OM is nearly equal to AB, so this implies you can write AB divided by A dash B dash is equal to OF divided by A dash F. Equation 3. Clear? Now comparing 3 and 1, we will get what? AB by A dash B dash equal to AO by A dash O, AB by A dash B dash equal to OF by A dash F. So comparing 3 and 1, we will get what? Comparing 3 and 1 now, from equation 3 and 1, we will get what? AO by A dash O equal to OF by A dash F. So this simply means AO divided by A dash O equal to OF. The A dash F can be written as A dash O minus OF, because this is A dash F which is written as A dash O minus OF. Clear? So what is OA? Here is OA, which is the object distance and it is measured opposite to the direction of incident ray, so minus U. What is A dash O? A dash O is the image distance which is measured along the direction of incident ray, so plus V. What is OF? OF is the focal length which is measured along the direction of incident ray, so plus F. So now replacing this AO will be minus U divided by A dash O is minus V, sorry plus V, is equal to OF is plus F divided by A dash O is plus V minus F. So now cross multiplying this, it will be minus UV plus UF equal to VF. Now dividing UVF on both sides. We will get what? This will be minus 1 by F plus 1 by V equal to 1 by U. So rearrange this, we will get 1 by V minus 1 by U equal to 1 by F, which is the required lens formula. Okay, so this is the required lens formula for a convex lens producing real image. Clear? Next we are going to discuss about case 2 for deriving the lens formula for a convex lens producing virtual image. Next case we are going to convex lens producing virtual image. Okay, so this is the convex lens. Let this will be the principal axis. O, F, 2F, F. So when the image will be virtual and direct when the object lies between focus and pole like this. So the incident ray will travel along this direction. The refraction it will pass through along this direction, so they will meet at somewhere here. So this will be the image. If this is A, B, this will be A dash, B dash. This is M, O, M dash. Clear? So now in triangle, similarly, now in the triangle A, B, O, A dash, B dash, O. In triangle A, B, O and A dash, B dash, O. This is A, B, O triangle and A dash, B dash, O triangle. Angle A equal to A dash 90 degree. O, angle O is common. So both triangles are similar. So we can write the corresponding sign ratios. AB divided by A dash, B dash equal to AO divided by A dash O. Equation 1. As AB shifted to OM and these rays are parallel. So AB as AB is nearly equal to OM. So in triangle AB is nearly equal to OM. So in triangle OMF and A dash, B dash, F. So this is the triangle OMF and A dash, B dash, F. This is the triangle. Okay. F is common and angle O equal to angle A dash equal to 90 degree. This angle and this angle is 90 degree. So both triangles are common. Triangles are similar. So the corresponding side ratios will be equal. So OM divided by A dash B dash equal to OF divided by A dash F. Clear? Okay. So as OM is nearly equal to AB, so this can be written as AB divided by A dash B dash equal to OF divided by A dash F. So this implies you can write AB divided by A dash B dash equal to OF divided by A dash F. What is A dash F? A dash F can be written as A dash O plus OF. So A dash F can be written as A dash O plus OF. Let it be equation 2, because this is A dash F, which can be simply written as OF plus A dash O. Clear? So now from equation 1 and 2 we get AB by A dash B dash equal to AO by AO dash and AB by A dash B dash equal to OF by AO dash plus OF. So from 1 and 2 we get AO by A dash O equal to OF by A dash O plus OF. Equation 3. Now what is AO, OF, A dash F? So what is AO? AO is the object distance which is measured opposite to it, so minus U incident ray. A dash O image distance minus V, and OF plus F. Clear? So now applying this AO minus U divided A dash O minus V is equal to OF plus F divided by A dash O minus V plus F. So cross multiplying this we will get minus UV plus UF equal to VF, dividing both sides with UVF. We will get minus 1 by F plus 1 by V equal to 1 by U. So this is 1 by V minus 1 by U equal to 1 by F. This is the required lens formula for a convex lens producing virtual image. Clear? This is the case 2. Next, third case for concave lens producing virtual image. Case 3. Thin lens formula for concave lens virtual image. Okay, so here this is the object and the rays goes like this, and this is the object. So this will be the image A dash, B dash, AB. Clear? Okay, so now shift this from this will be MO. So this is the parallel object shifted to MO. Clear? So in triangle ABO and A dash B dash O is common, and angle A equal to A dash equal to 90. So ABO this triangle and A dash B dash O this small triangle. O is common angle, A dash A both have 90 degrees. So these two triangles similar. The two triangles are similar. So you can add AB divided by A dash B dash equal to AO divided by A dash O. Let it be equation 1. Clear? As AB is nearly equal to MO. So in triangle MOF and A dash B dash F triangle, MOF this triangle and A dash B dash F this small triangle, angle O equal to angle A dash equal to 90 degree and angle F is common. So triangle MOF and triangle A dash B dash F are similar. MOF, A dash, B dash, F. This small angle and this large triangle are similar, so you can write MO divided by A dash, B dash equal to OF divided by A dash, F. Or this implies as MO is nearly equal to AB, you can write AB divided by A dash, B dash equal to OF divided by A dash, F. Or this implies you can write AB divided by A dash, B dash equal to OF. AF, A dash, F can be written as OA dash, OF minus OA dash. So A dash, F can be written as OF minus OA dash. Clear? Equation 2. So what is from 2 and 1 we will get what? So from equation 2 and 1 we will get from 2 and 1 we will get here AB by A dash, B dash is equal to AO by A dash, O, and AB by A dash, B dash equal to OF by OF minus OA. So from 1 and 2 we will get AO by A dash, O equal to OF divided by OF minus OA dash. So what is AO? Here AO is the object distance measured opposite to the direction center minus U, OA dash minus V, and OF is also minus F. So AO will be minus U divided by minus V equal to minus F divided by minus F plus V. So now cross multiplying this we will get minus UF minus UV equal to minus FV dividing UVF. We will get what? Minus 1 by F minus 1 by V minus 1 by F equal to minus 1 by U. So this will be 1 by V minus 1 by U. Sorry, I think I have missed something here. It will be, just a second. Okay, so here it will be plus, because this is minus UF plus VU, because this is negative will get cancelled. So minus F into U minus UF plus V into U, that is plus UV equal to minus VF. So dividing on both sides by UVF it will be minus V, so it will be plus 1 by F equal to minus 1 by U. So by rearranging this we will get what? 1 by V minus 1 by U. So this implies you will get 1 by V minus 1 by U, taking this to the right hand side equal to 1 by F. So this is the required lens formula for a concave lens producing virtual image. Clear? So these are the three cases: how image is formed through concave and convex lens, and how to derive the thin lens formula. Clear? And in each case you have to remember the formula, what is V, what is U, and what is F, and all are used during numerical solutions by using their sign convention. Clear?